Okay, here's the problem solving video for problem 531. Says find V0 using Thevenin's theorem. You can see our circuit there. We're going to be utilizing the problem solving strategy for Thevenin's theorem, which is found on pages 185 and 186. Step 1 says remove the load and find the voltage across the open circuit terminals. And you can use all techniques to do that. So if we're going to find the voltage V0, we're going to consider the 1 kilo ohm resistor as our load. We're going to find the Thevenin equivalent circuit, which will be the following. We'll label these terminals A and B. Then we're going to hook our load 1 kilo ohm up to that circuit and find our voltage V0. So our task is to find the Thevenin equivalent for all those elements outside the red box, and we need to find V open circuit in our Thevenin. And in this case, we don't have any dependent sources. So step 2A applies, where we can make those independent sources zero by replacing voltage sources with short circuits and current sources with open circuits. We'll find the resistance using combination. So let's start off calculating the open circuit voltage. So if we remove our 1K load, that is the resulting circuit. We've removed the 1 kilo ohm load. We've labeled the terminals A and B. We're now going to find V open circuit. If we make a few quick calculations, we know that current is 2 milliamps. So we know that voltage is 4 volts. Okay? So really, if we're going to find V open circuit, looks like we're going to have to use this loop. So we need to find the voltage from here to here. Okay? And we can do that a number of ways. We've discussed several techniques. Nodal analysis and loop analysis. Let's look at those. For instance, if we did mesh analysis, we have 3 meshes. We have 2 current sources, which leaves us with 1 unknown mesh current. If we do nodal analysis, if we were to pick the bottom node as a reference, then we would have 2 node voltages, V1 and V2, and if we found V2, we really have another node voltage here, that's V3, but we know that V3 is equal to 12 volts. Then once we have V2, when we have the open circuit, let's apply nodal analysis to this problem. And what reason we'll do that is once we find the voltage V2, the open circuit is 4 volts plus V2. So using nodal analysis, so we're going to have 2 equations. So if we apply KCL to this node, for instance, we'll have V1 over 3K plus V1 minus V2 over 6K. Those 2 currents are leaving. We've got another current leaving, 1 entering. So on the right hand side we'd have 8 milliamps minus 2 milliamps, or 6 milliamps. Okay, so we can simplify this equation. If we'd like, we could write it as 1 over 3K plus 1 over 6K times V1 minus 1 over 6K times V2 is equal to 6 milli. Now if we go in and apply KCL to this node, we'd have V2 minus V1 over 6K plus V2 minus 12 over 6K. So the first term is the current leaving the node in that direction. The second term is that. Now if we look, there's 2 milliamps entering that node. Okay? There's 2 milliamps entering that node. So here are our two equations to solve. And in fact, probably would have been easier to have solved this with mesh analysis. Doesn't make any difference. You could do it either way. Here we picked nodal. We wanted to find the voltage V2. If we did mesh, we'd have one unknown. Then you'd have that mesh current times 6K plus 12. If you solving yields V2 equal to 21.6 volts. So then VOC is 4 plus 21.6 to give VOC 25.6 volts, and you would get the same answer if you had selected mesh analysis. In fact, here mesh would have been a little simpler. We'd only had one equation. We should be able to do it either way. Now let's calculate R Thevenin. If we go into our original circuit, and I'll show it here real quick. If we set all those sources, really turn them off, this becomes an open, this becomes an open, this becomes a short. The resulting circuit is as shown. Okay, so now we have these two resistors in series for a 9K. So really we have a 9K resistor in parallel with a 6K. So R Thevenin is 9K times 6K over 9K plus 6K plus 2K. Now the 9 is a series combination of those two. So R Thevenin turns out to be 5.6 kiloohms. So now let's draw our Thevenin equivalent. We have a voltage of 25.6. We have a resistance of 5.6 kiloohms. Now we reconnect the 1 kiloohm resistor. There's the voltage V0. So by voltage division, V0 is 25.6 times 1K over 1K plus 5.6K. And that gives us V0 is 3.88 volts.